Hello and welcome to these video notes where we're going to look at expressions that are dividing with exponents. And so let's take a look at our first problem, 5 to the power of 3 divided by 5 to the power of 2. Now this could be something you just plug into the calculator, or we could go to some definitions like 5 to the power of 3 is 125, 5 to the power of 2 is 25, and 125 divided by 25 is 5. If you didn't know that, that's okay, that's what they invented calculators for. But I want to show you another strategy. Fractions are division problems, and so another way that I like to solve a problem like this is I like to think of things in the numerator as multiplication parts of the problem. So I might call this a multiplying 5, and in fact there's 3 of them. And then in the denominator are what I like to call dividing 5s. After all, a fraction is a division problem. So even though these 5s are being multiplied together, I'm going to consider them dividing 5s because they're on the denominator, and you divide by whatever's on the denominator. And in the numerator, these are my multiplying 5s. But if you multiply and divide by the same thing, then those cancel out. If I have a number and I multiply it by 5 and then I divide the answer by 5, I'm back to where I started. And so check out what I can do. I can cross out a multiplying 5 and a dividing 5. And cool, one less problem to worry about. And you know what? I can do that again. One multiplying 5 cancels out with one dividing 5. And look what happened. I have no more dividing 5s. All that I have left is a multiplying 5 in my numerator, and that's what I'm going to write. My answer is 5 over what? Well, a common answer might be 0, but that's incorrect because, well, you might expect that there's no 5s, therefore it should be 0, right? But no, and because secretly there's a times 1 here. 1 times 5 times 5, that's the same as 25, right? If that had been a 0, if I had said 0 times 5 times 5, that wouldn't work. That's still 0. So when we're canceling things with like multiplication, our default value should be 1. And 5 over 1, yeah, that's 5, exactly like we said before. So keep that in mind. Our numerator is full of multiplying factors, and our denominator is full of dividing factors. And so if I were to draw this problem, I might do something like this. And look what we got. 4 multiplying 5s, so to speak, and still 2 dividing ones. And so I could go through that same process. 5 to the power of 4 divided by 5 to the power of 2. Well, if I cancel one multiplying and one dividing factor, and I do so again, then I am left with 2 5s in my numerator, 2 of these multiplying 5s. And that should get me 25. 25 over 1, which is 25. And then once we get good at these problems, we can probably ignore that step, skip over it, and just skip straight to 25. And this works, this is great, but writing out all these 5s or whatever factors you're working with can be time consuming. And so there's one more little trick up our sleeves, one more rule that we can learn, and that is the quotient of powers property, which states that when you are dividing 2 of the same base, and no matter what their exponents are, I can subtract their exponents, and it would look something like this. 5 to the power of 4 minus 2. That is equivalent to 5 to the 4th divided by 5 squared. And, well, 4 minus 2, that's just 2. And check it out, that's also 25. 5 to the power of 2 is 25. So that's another way that you could solve this problem. So we've now seen 3 ways to do it. 1, you can just do the calculation. 2, you can write out all the factors individually. We got the multiplying factors and the dividing ones, and then cancel what you can. And then 3, we can use our new rule, our quotient of powers property. But I want to urge you to be careful. It's really, really easy to make this mistake. And let me be clear here, this is a mistake. This does not equal that. 5 to the power of 2 divided by 5 to the power of 5 is not 125, and it can't be. 5 to the power of 5 is bigger than 5 to the power of 2. How could I get 125 from dividing a small number by a big number? It just doesn't make sense. You can't do that. And so the mistake here is switching them around. Notice how 4 was my exponent from the numerator, and that came first. But here, 5 was my exponent on the denominator, and that comes first in this version. I guess I can call it version of the work, this incorrect version of the work. And that's a mistake that I see all the time, and that's why the quotient of powers property is one that's really dangerous. And I actually kind of suggest that maybe you should try it this way, writing out all of the factors and canceling the ones that you can, at least to begin with, because I think it's a bit safer and more consistent in finding the correct answers. So the correct way of doing this is seeing that there's 2 5s in the numerator, 2 multiplying 5s, and then there's 5 dividing 5s. And then once we see that, we can cancel, and do so again. And check it out, we have 3 5s in the denominator, 3 dividing 5s. So our answer was not 125, our answer was 1 over 125. We're still dividing by 3 5s, that's why it should be in our denominator. And so this is the correct way to apply this quotient of exponents property. So let's see this with a couple more examples. In our next examples, we have a to the power of 5 divided by a, which is a to the power of 1. And what we can do here is list off of our multiplying a's and our 1 dividing a. After all, a to the power of 1, a is simply a to the power of 1, so there's our 1a. And so I have 5 multiplying factors and 1 dividing factor. So I can cross 1 off of each side of our fraction, and I end up with 4 a's in the numerator, 4 multiplying factors. And so I can call this a to the power of 4. And then since there's nothing left on the denominator, I can call that 1. And this is just a to the power of 4. This is one that it's fairly safe to use the quotient of powers property. You would just say that this is a to the power of 5 minus 1, because after all, there is a hidden 1 here that we don't write, but it is there. And so 5 minus 1 is 4. And that's how we get that answer. So let me fix that. So our next problem, we could do the same thing, but again, this is one where the power on the denominator is bigger. It's really easy to get that switched and call this b to the power of 1, which if you don't see why, you will soon, when actually it should kind of be the opposite. So let's check it out. We have 3 b's in our numerator, 3 multiplying factors, and 4 dividing ones. And so we can start canceling 1 and 1, 1 and 1, 1 and 1, I have 1b left, and it is on the denominator. And so this is 1 over b. And yes, it is b to the power of 1, but I wouldn't actually write that. It's just b. And this can't be simplified anymore. That's the best I can do. 1 over b. All right, and that brings us to this problem. This will be our second to last. We will have one more kind of complicated looking example after this. Let's take a look at this one here. And so this is a problem that has a lot of stuff going on. It has numbers, the 2 and the 4. It has a and it has b. So what to do in a situation like this? Well, what you can do is break this into pieces. And so I can deal with just the numbers first, for instance, 2 over 4, and just ignore the a and the b for now. Well, 2 over 4 is a fraction that can be simplified, and I know that because 2 and 4 are both even. So I'm going to divide them both by 2. And I can get 1 over 2, easy. Next up, we have our a's, and I have 5 a's on our numerator, as well as 1 on my denominator. I can do a quick cancel, and I end up with 4 a's on the numerator. And then last but not least, I can do the same with the b's. I have 1b on the numerator, and I have 2 on our denominator. And likewise, just like the a's, cancel, cancel, and I end up with 1b on my denominator. And so you see how you can just deal with each part individually, and then we can put it all together. So I have 1 over 2, I have a to the 4th over 1, and I have 1 over b. So you see how each part, I just took the answer and I put it back, and then let's do some simplification. 1 times a to the 4th times 1. Well, 1 times anything is that thing, and I did that twice, so this is just a to the power of 4. 2 times 1 is 2, and 2 times b is 2b. And so I have my answer. 2a to the 5th b over 4ab squared, which, man, these things start to become a handful just to say, is a to the 4th over 2b. There we go. We have one more problem to do, and it is going to be another one of these kind of complicated things with lots of stuff going on. So let's take a look at it. All right, on our last example, we got this kind of monstrosity, and this can be really intimidating, and a lot of students struggle with something like this because it just looks scary, and they, I think, psych themselves out a little bit. But we're going to follow the same steps. We're going to do one part at a time until we get our answer. So just like before, I'm going to look just at the numbers. On my first fraction, which I got multiple fractions being multiplied together. Don't freak out. On my first fraction, I have 2 over 3, and on my second fraction, I have 6 over 4. And one of the nice things, even though this is a fraction, fractions are scary, multiplying fractions is easy. You just multiply the numerator and multiply the denominator. So yeah, just 2 times 6 and 3 times 4. No big deal. And let's see what happens. 2 times 6 is 12. And then 3 times 4, that's also 12. So check out what happens in this problem. This is kind of nifty. 12 divided by 12 is just 1. And since this is multiplication, you never have to write a 1, unless everything cancels. But I don't think that's going to happen. If everything cancels, you would have to write something, in which case you would write a 1. But as long as there's anything else in the problem, we don't have to say times 1. So this is pretty much gone from our problem. Nice. We move on, and we take a look at the x's next. So next up, I don't like that color. I'll use yellow. I don't remember what I used before. Up next, we'll take a look at the x's. I have 1 from my first fraction, and I have 4 from my second, all on the numerator. Okay, so 1 and 4. 1 and 4. So it checks out. I also have 1 on my denominator and then 6 more from the other fraction. So here's my x's, and now I can start canceling. Cancel, cancel, and keep doing so. Make sure that you pair up one numerator, one denominator being canceled. And there we go. I've canceled 5 multiplying factors and 5 dividing factors. I'm left with 2 dividing factors, and so this is going to simplify to 1 over x squared, because there's 2 x's. And then finally, that leaves us with the y's. I have 3 on the numerator and 2 more on the numerator. So there's 5 y's altogether. 3 and 2 make 5 after all. I have 1 on the denominator and 3 more on the denominator, so I should end up with 4 here. And we can start canceling. 1 multiplying and 1 dividing factor. Same way all the way down, and I end up with just 1 y on the numerator, 1 multiplying factor of y. And so I end up with my simplified version of this. This is just 1, which I don't really have to write, times 1 over x squared, times y over 1. So there we go. There's 1 over x squared, there's y over 1, and Technically, I am multiplying by another 1 here, but I don't have to do that. And then 1 times y is y, x squared times 1 is x squared, and my expression simplifies to y divided by x squared. So there we go. That's the strategies that we're going to be using to solve problems using the quotient of powers property. And I hope that made sense. I'll see you next time. Bye-bye.